So in our previous lecture, we learned the fundamentals of Bode plot, and we learned how to draw Bode plots on semi-log paper. And we did an example of drawing Bode plot of a system with transfer function gs equal to 1 upon s, and the Bode of this type of system was given as shown in the figure here. Now we'll today talk about the Bode plot of a first order system. So as we remember that the transfer function of a first order system is given by gs, which is equal to 1 upon tau s plus 1. So this is a general form of representation of a first order system, and from this we have things such as time constant of the system given by tau. The frequency response function is obtained by substituting s equal to j omega, that is g j omega 1 upon tau j omega plus 1. So I repeat again that whenever you are going to perform frequency domain analysis, the basic three rules will be applied to all the approaches first, and this is the rule number one that we have discussed in frequency response analysis when we started talking about this unit. And thus the magnitude is given as, if you find the magnitude of this function, so the magnitude is given by 1 upon under root 1 plus omega square tau square. In decibels, this can be written as 20 log to the base 10 of magnitude as follows. So we obtain the magnitude in decibels. Now when omega is much less than 1 upon tau, now if you look at the function here, so we are going to draw a Bode plot of a first order system, and there's a note that mentions that this method, so as I told you before, that Bode plots drawn by hand are a straight line approximation of the actual plots. So if you in fact draw the Bode plot using softwares like MATLAB, you will be obtaining the exact plots. But when you try to draw the Bode plots by hand, by the approaches that are being mentioned here, then they will be the straight line approximation of the actual or exact plots. So this is the reason why they are the approximate plots or the approximations, because there are certain assumptions that we'll be taking when we draw Bode plots by hand. One of which is that you, for example here, because you see this particular function, you see that there is an expression under root 1 plus omega square tau square. So we are going to assume this. We are going to make this function under root 1 plus omega square tau square equal to 1. So this assumption that this expression, this term under root 1 plus omega square tau square will be close to 1, it holds when omega, the value of omega is much less than 1 upon tau. So if you're going to substitute a value which is much less than 1 upon tau, then what this expression, this omega square tau square, will be closer to 0, which makes the term under root 1 plus omega square tau square close to 1. So that function under root 1 plus omega square tau square will be close to 1 only when we are going to assume omega much less than 1 upon tau. And then omega square tau square is negligible compared to 1, and so the magnitude now can be written as 20 log to the base 10 of 1, which is 0 decibels, which means that the magnitude plot, so we know that magnitude and phase are the two, and their combination are termed as Bode plot, and we are trying to conclude about the magnitude part of the Bode plot by the assumptions. So the magnitude part for omega much less than 1 upon tau is 0 dB. That is a straight line with a magnitude plot of 0 dB. Now if we assume for frequencies which are higher than 1 upon tau, so frequencies much higher than 1 upon tau, we have omega square tau square much greater than 1. In that case, what we assume is 1 plus omega square tau square equal to omega square tau square, and the magnitude will be reduced to. So if you again look at this particular expression, so if you're going to assume omega much greater than 1 upon tau, in that case the term 1 will be negligible compared to omega square tau square, and thus this particular term in the under root, that is under root 1 plus omega square tau square, will reduce to under root omega square tau square. So in that case, this particular expression or term will be reduced to under root omega square tau square. So this is going to hold when we assume that omega is much less than 1 upon tau. And in the previous case, we assumed that this is equal to under root 1 with omega square tau square negligible when omega is much less than 1 upon tau. So we have now omega, when this term is much greater than 1, the magnitude now reduces to 20 log 1 upon under root omega square tau square, which can be written as 1 upon omega tau, and thus this comes out equal to minus 20 log omega tau, which is a straight line. So in this case, you had a value 0 dB, so which means that it's a straight line for all the frequencies. When omega is much less than 1 upon tau, you'll be having a straight line with magnitude plot 0 dB. But when you assume omega much greater than 1 upon tau, in that case, if you look into this expression, so we talked about drawing the curves or drawing the lines on Bode plot on the semi-log paper and identifying what slope it will exhibit. So if you look into this expression, the slope of the line is minus 20 dB per decade, and the slope with minus 20 dB holds for omega much greater than 1 upon tau, and this will be in fact intersecting 0 dB line at omega equal to 1 upon tau. So this can be verified by substituting omega equal to 1 upon tau. So if you're going to make this particular expression 1, and this is only possible when omega will be equal to 1 upon tau, and thus what you're going to get is 20 log to the base 10 of 1, which is 0, and thus this line will be intersecting 0 dB when omega is 1 upon tau. Now, after obtaining the magnitude or concluding about the magnitude part of the Bode plot, we'll move towards the phase part of the Bode plot. And we know that in order to obtain the phase angle of the system, it's quite easy. And since we studied that tan phi using the same expression that we see here. So if you look into this part, so from this we obtain the magnitude, and then we can easily obtain the phase of this particular expression by looking into the terms that are present in the numerator as well as denominator. So from numerator we won't be having any, we don't have any contribution in the angle from numerator terms, while if you look into the denominator you have an angle contribution that will be negative because the terms are in the denominator, and that will be equal to tan inverse of tau omega by 1. Or in other words, you can say that tan phi is equal to minus omega tau upon 1. So for lower frequencies, the phase angle approaches 0. So if you talk about omega much smaller, then that case the angle will be 0. At higher frequencies, it means that we'll be having this part infinity. So in that case, the phi will approach 90 degrees. And there is a term called as corner frequency in Bode plots. So these are the frequencies at which the Bode magnitude plot takes a turn in, is called the corner frequencies. So this should have been mentioned where we talked about the magnitude plot, and I'll explain this in the actual plot. So corner frequencies are the frequencies where the magnitude curve will be taking turns. For example, if you look into this Bode plot, so this is the magnitude plot and this is the phase plot of the first order system we just discussed. And as we saw that there was a 0 dB straight line for omega much less than 1 upon tau, and then we have a line with a slope of minus 20 dB per decade when omega was much greater than 1 upon tau. So in fact, this part comes from the assumption of omega much less than 1 upon tau, while the second part, this part, we were assuming that omega is much greater than 1 upon tau. So this is why we say that these are the approximations. And one thing, the corner frequencies, okay. The breakpoint or corner frequency is the point or the frequency at which the curve takes the turn. So this is the point where we see that the curve is going to take the turn. So the slope of the curve or the line was 0 dB per decade here. And after this point or this particular frequency, you have slope minus 20 dB per decade. Now, the reason that we say it to be an approximation is that if you try to obtain the actual curve, so you say that for omega much less than 1 upon tau, the line is having a slope of 0 dB per decade. Likewise, for omega much greater than 1 upon tau, the line slope is minus 20 dB per decade, which means that they are not going to hold very well when omega is closing 1 upon tau at this particular frequency. So when omega will be close to 1 upon tau, these two assumptions will not be pretty accurate, which means that the exact point at this place will be located somewhere above or below, depending upon what value of zeta the system has. So you can in fact, using MATLAB or other simulation software, draw the Bode plot of the first order system and observe that the actual or the exact Bode plot differs from the straight line approximations of the Bode plot drawn by hand. In fact, if you try to substitute omega equal to 1 upon tau in the magnitude expression of magnitude, so what expressions of a magnitude we got is here. So if I substitute 1 upon omega equal to 1 upon tau, we get this as 1 upon under root 1 plus 1. So this makes 1 upon under root 2, which is not 0. So it will be having some finite value, some negative value, which means that the exact point should be lying slightly below the 0 place. So this is 0, and the actual point at omega equal to 1 upon tau will be somewhere below it. So not very far, which means that the curve will be reaching the point at certain slope which will be very small, and then will be going towards infinity at taking a slope of minus 20 dB per decade. Likewise, we concluded about phase plot for different values of tau. So in fact, phase plot can be easily drawn by by forming a table like this. So we can form a table where we choose randomly the values of omega and calculate the values of phi by substituting the values of omega. For example, shown over here is the value calculated corresponding to omega equal to 0.1 divided by tau. So if you assume that omega is 0.1 divided by tau and looking into the expression of the phase angle, we see that phi is equal to tan inverse of minus omega by tau. So if we are going to substitute in place of omega the value 0.1 by tau, so what we get is minus 0.1, and phi, the angle phi will be equal to minus tan inverse of minus 0.1, which will be close to 0, and thus tan phi will not be exactly 0 but will be having a value close to 0 and will be negative. So it will be something negative but close to 0. So this is not going to be exactly 0 at 0.1 by tau. Likewise, in order to obtain other values, we can substitute other values like 1 upon tau. So if we are going to substitute this in the phase, then we get phi as tan inverse of minus 1 upon tau into tau, which is minus tan inverse of minus 1. So now we again are going to have some finite value. So at 1 upon tau, we'll be having certain value here. Then for higher values of tau, we will again have a straight line which will be minus 90 degrees. So for all values of omega, sorry, not tau, for all values of omega much greater than 1 upon tau, we're going to have an angle close to minus 90 degree. And for omega infinity, that will be exactly equal to minus 90 degree. So this is how the plot for phase looks like for first order system. And in fact, the way the approach that we have taken here, the assumption that for lower frequencies phase angle is 0 and for higher frequencies phase angle is 90 degree. So this is a bit difficult approach. An easier approach is to obtain the table and substitute the values of omega for different frequencies, for example 0.1, 1, 10, 100 and so on, and keep on computing the value of phi for those values of omega assumed. Now we talk about the Bode plot of a second order system. And if you remember that the transfer function of a second order system was given as gs equal to omega n square by s square plus 2 zeta omega n s plus omega n square. So this is the standard form of second order system, and it is something that we kept on discussing right from unit 3rd. I guess there should be no doubt in how we obtain this transfer function. And of course, one thing that I wanted to mention always, so gs is normally is represented for gain of the forward path, while this particular transfer function we obtained was for g over 1 plus gh, which is the closed loop transfer function. So since most of the books have written that the transfer function of a second order system is given by gs, so this gs is not the same g where we have g in the forward path forward path and h in the feedback path. So this g is different from this g. In fact, the g that we are talking right now is the transfer function g over 1 plus gh. Since books have used this particular term for representing the transfer function, so we will also be writing the same term. And the important thing to see in order to know that whether this is the open loop transfer function or a closed loop transfer function or forward path transfer function or overall transfer function is to look into the expression that is into the statement that is written. So the statement written is the transfer function of second order system, which means that we are talking about the closed loop transfer function, and thus GS is the closed loop transfer function accompanying the forward path gain as well as feedback gain. The frequency response function is obtained by substituting s equal to j omega. So this is the rule 1 that will always be applied, and that gives us j omega equal to. So we're going to substitute all the values of s, or we're going to replace s by j omega, and we obtain this particular expression. And thus the magnitude is given as, so if you're going to obtain the magnitude of this term, this will be obtained by forming the perfect square of the expression in the denominator, then taking the root of it. So in fact, we took the term omega n square in the denominator of the, we took the term omega n square below the denominator polynomial. And finally, we obtain this particular form x square plus y square. In decibel, this can be written by taking the term 20 log to the base 10 of this magnitude. So this is the magnitude in decibels. Now, again, we're going to make some assumptions. If you look into this expression, we see that if omega upon omega n is much less than 1, or in other words, omega is much less than omega n, in that case, this particular term 1 minus omega by omega n whole square reduces to 1. And likewise, this term is, if it is much less than 1, so it means that this will be again assumed 0. So what we are left in this particular term is, in the denominator, is simply under root 1 for omega upon omega n much less than 1, or omega is much less than omega n. So the magnitude that we get is 20 log to the base 10 of 1, which is 0. So if we try to imagine about this on the Bode magnitude plot, so we have omega on the x-axis and decibel on the y-axis. And since for omega much less than omega n we can assume if it is not given in the question in any numeral form. So if we assume that omega n is somewhere on the x-axis here, then for omega much less than omega n means that all the frequencies which are lying on the left side of the omega n line, then in those plot which lie on the left of the omega n will be having the slope 0 dB. That is, they will be having straight, that will be they will be a straight line, and the slope will be 0 dB per decade. While if you assume omega much greater than omega n, in that case the magnitude, now we are talking about frequencies which lie on the far right of omega n. So the frequency, the magnitude can be obtained as minus 20 log to the base 10. So looking into the previous expression, if you're going to take the value of omega much greater than omega n, which means this particular expression will close to infinity, and in that case again we'll be having this as infinity. So if you looking into this expression, so we have one very small to the expression omega by omega n. Since omega is much greater than omega n, in that case this can be assumed infinite. So we have infinite square, then we have a negative sign which makes it as again a minus infinite. But if you look into the outer braces, we have again a square which makes minus infinite square plus infinite. So this will become plus infinite, and then you again have a plus infinite here. So the values are positive, first of all. The second thing is that one will be discarded because this becomes negligible in terms of omega by omega n. We are not going to substitute infinite here because we are interested in different values of omega that would be high. So not exactly infinite. Infinite is one of the frequencies that we will be concluding about the plot at, but for omega not infinite but larger or also being taken into consideration, and that is why we are not going to assume this infinite, but we will say that for omega much greater than omega n, we are going to have the expression here as under root omega by omega n square, or again to the power 4. So this terms gets omega upon omega n to the power 4, and plus you're going to have another term plus 2 zeta omega upon omega n to the power 2. So this term can be again considered negligible to the term omega by omega n to the power 4. So we're going to discard this term, and the term that we are going to now have from this expression, so when we consider omega much greater than omega n, we are going to have this as 1 upon under root omega by omega n to the power 4. And this can further be written as 1 upon omega n square. And again, if you're going to take this term into the denominator, so we will have a negative sign as minus 20 log to the base 10 omega by omega n square. So we have a negative sign because we brought this term from denominator to numerator. In fact, if you talk about the slope of this line, so we have a power of 2 here. So if you're going to take this 2 on left side, then slope, this value can further be written as minus 40 log to the base 10 omega by omega n. So in order to conclude about the slope or plot the line, you are supposed to remove this 2. You're going to take this 2 here, and this makes minus 40. We did this because we are interested in plotting decibel versus omega and not omega square. So we are plotting decibel versus omega. That is why we want this expression to be written in terms of omega only, not omega square. And thus this makes the slope of the line as minus 40 dB per decade, which means that for omega that are much greater than omega n, we'll be having a line with slope minus 40 dB per decade. So if we talk about the phase of the system, which is tan inverse of, of tan phi equal to minus b upon a. So using the same expression, we can obtain this. Since we have the expression in the denominator, that is why we have negative sign. And in the numerator, if you look into the expression, yes, here. So you first of all will be trying to make this into a plus jb form. You'll have to bring this into a plus jb form, and that can be done easily by looking into this expression. So we have this can further be written in a plus jb form as omega n square minus omega square, which becomes a plus j 2 zeta omega n omega. In fact, if you divide the numerator and denominator by omega n square, so this can further be written as this becomes 1, this becomes minus omega by omega n square, and this becomes omega by omega n, and this also becomes 1. So now what you're left with is a, which is 1 minus omega square upon omega n square, and b, which is 2 zeta omega by omega n. So this will be contributing a negative angle. So we'll be having tan of phi equal to minus, because the term are present in the denominator, that is why we're going to take a negative sign, and b upon a gives you 2 zeta omega by omega n divided by 1 minus omega square by omega n square. Or phi can further be written as tan inverse of minus 2 zeta omega by omega n, 1 minus omega square upon omega n square. So this is what is written here. So you have tan phi equal to minus 2 zeta omega by omega n, 1 minus omega by omega n square. Now for lower frequencies, look, these are the assumptions that we are making because we don't have the exact transfer functions of first order, second order system. We are having the abbreviations for time constant and frequencies and zeta. We are not given the values of zeta and omega n till now. So you will be given questions where zeta and omega n will be specified. So you will be talking about values taken in numerals, and that is why there will be no need for making assumptions for phase angle. So you will be straightforward plotting the table that I just told you in the previous example, and from those table you will be computing the values for the phase angles for different values of omega. So that approach is a bit easier and accurate than this one. So the assumptions that we make here is that at low frequencies, and we are making this assumption because of the reason that we have no numeral form of zeta and omega. We don't know the values of zeta. So we are just generalizing the problem. And for lower frequencies, that is for omega much less than omega n. If you look into this expression, you will be taking this value, or this will close to 0, which means you are left with 1 in the denominator, and this will become 0. So you're going to have tan phi equal to 0 upon 1, which makes the angle 0. For higher frequencies, the phase angle will reach 90 degrees. So for higher frequencies, you'll be going to have this as negative and this one as negative. In fact, this will be larger than the numerator. So this will make the expression infinite. So the plots that you will be obtaining for different damping ratios are shown, and this in fact can be concluded from MATLAB as well. So in fact, these are the plots that are simulated. These are not they are not the straight line approximations, not by hand. So they are the plots that are obtained by the software. So you can see that for different values of zeta, you're going to have different types of forms. But the angle for omega much greater than omega n, or when omega approaches infinity, you will have slope as minus 40 dB per decade. So the slope is minus 40 dB per decade at this place when omega is much less than omega n. Likewise, when omega is uh, here omega is much greater than omega n. When omega is much less than omega n, in that case you're going to have slope 0 dB per decade. But when you close to omega n, so omega n is somewhere here. So when you are close to omega n, in that case you will be having the exact plot shown. Had you drawn this by hand, so the two lines, this line and this straight line, where these two lines will be intersecting will be the point which you would have shown on the Bode plot if you drew it by hand. Likewise, for omega much less than omega n, you have 0 degree, and for omega much greater than omega n. In fact, there is a slight correction. Here is that we are going to approach an angle of minus 180 degree for omega much greater than infinity. So the mistake that we committed was here. So this should be 180 degree, not 90 degree. And this can be easily verified if you're going to substitute omega equal to omega n. Then what you're going to get is 2 zeta into 1 divided by 1 minus. This turns 1 and you get this whole expression as 0 when omega is equal to omega n. And thus tan phi for this case when omega is equal to omega n, tan phi turns infinity, which means phi will be equal to minus 90 degrees. So this holds for omega equal to omega n. But if you're going to take frequencies greater than omega n, let's say 2 omega n or any other value. So for omega greater than omega n, you are going to have the angle of phi greater than or less than minus 190 degrees. So since we're talking about negative angles. So we'll be having omega close to minus 180 degree when omega is much larger than omega n. And that is why the plot shown over here approaches minus 180 degrees when omega is taken greater than omega n. And for different values of zeta, so in the next class I'll try to show you that how this plot closer to omega n varies. One thing more, since you, in fact this graph was drawn from a book, and that is why that book has taken, instead of omega, they have assumed this x-axis as omega by omega n. So the nature of the plot will not change if you're going to instead use omega in place of omega by omega n. So if you're going to plot this curve for x-axis taken as omega by omega n, then this line will be 1, just shown here. But if you're going to plot this curve for omega only, in that case, instead of writing 1 here, you will be writing omega n. So when omega will be equal to omega n, you're going to have these curves taking turn like this. So that's enough for today. And if you have any questions or doubts, you can post me or you can ask me in later classes.